we're going to begin by working on graphing the tangent curve. I've filled in a lot of the function values, and there's no mystery in how we get them. It's just we use the fact that tangent is sine over cosine. Use this fact right here, and using that fact in the unit circle, it's easy enough to see that at negative pi over 3, the value of tangent will be negative root 3. Now, one difference between the tangent function and the sine and cosine function is that while also periodic, which is not surprising, its period is pi and not 2 pi. So you will get the full range of values of tangent just by going from, we could say let's go from 0 to pi, but we will get a nice continuous smooth curve if we go from minus pi over 2 to positive pi over 2. So that's what we're going to do. In essence, it's sort of like let's graph, and we say from minus pi over 2 to pi over 2, minus pi over 2 meaning going backwards. So like at basically the right half of the circle. So from the bottom of the circle all the way up to the top of the circle. And that'll give us one full period of tangent. So we have, let's see, at minus pi over 3, at minus pi over 2 it's not defined. Let's talk about y. So tangent of tan x is sine over cosine, right? Now we know that sine and cosine are bounded, right? They are bounded between, they're always between -1 and 1. So it might seem that if this is bounded, that tangent should itself also be bounded, but in fact it's not. Because one way that a fraction could blow up I guess one way is certainly to have the numerator just get huge. But the other way is to have the numerator get super crazy small. Like if I take 1 and I divide it by 1/10, we get 10, right? If I take 1 and divide it by 1/1,000,000, we get 1,000,000. And as the closer to 0 the denominator gets, the bigger the fraction is. So at the bottom of the circle, at the bottom of the circle, cosine is equal to 0. So as we approach negative pi over 2, cosine shrinks to 0. That makes our fraction blow up. Now, cosine shrinks to 0, sine becomes negative, so it's actually blowing up in the negative direction. It's becoming hugely negative. Then at pi over 3, or negative pi over 3, we're at negative root 3, which is about negative 1.73. So that is, I don't know, maybe about there. At negative pi over 4, and I wrote pi over 2 here in the notes, but that should definitely be a pi over 4. At negative pi over 4, the value of tangent is negative 1. At negative pi over 6, it's 1 over root 3, which is a little beyond negative a half, maybe right there. At 0, we're at 0. And I'm just taking these values that I put in that first column, the values for tan x. At pi over 6, we're at positive 0.577, so maybe around there. At pi over 4, we're at 1. At pi over 3, we're at 1.73, so maybe there. And then at positive pi over 2, again at positive pi over 2, that's the top of the circle. And at the top of the circle, cosine is 0. So the closer we get to the top of the circle, the bigger and bigger tangent becomes because we're dividing by crazy small numbers. So we get these, the behavior at negative pi over 2 and pi over 2, I drew these like dotted lines here. I don't know how well they showed up on the printout, but these are supposed to be dotted lines. They're vertical asymptotes, and those will happen anytime in a graph when you get close to dividing by 0. And the dotted line itself is not a part of the graph, but it's going to help guide us, it's going to help guide our sketch. Because the closer I get to pi over 2, say, it's going to blow up. So it's just going to go, get as high as you want it to get the closer we get to that dotted line. And then similarly, the closer we get to negative pi over 2, it blows up in the negative direction. So there's a nice smooth curve. And this, if we kept graphing it, it would just be the same shape that occurs over and over again with a period length of pi. Now, if we graph 2 pi, well, certainly when I get close to dividing by 0, I'm still getting close to dividing by 0, so that is undefined and undefined for the 1/2 pi. Here, all we're going to do, if we're taking 2 times tangent of x, we're just going to double these values. So we have -2√3, which is about 3.46. This will be -2. This will be -2 over √3, which is about -1.15. 2 times 0 is obviously 0. And then we have the same values repeated on the other side of 0 for the positives. So let's fill in, let's plot these points, and then we'll work on the last column. So -3, at negative pi over 3, we're at -3.46, so that's pretty close to 3.5. At negative pi over 4, we're at -2. And negative pi over 6, we're at -1.15. So close to there. And then it goes through 0, 0 again. And then we have the same kind of basically like the mirror image on the opposite side for the positive values. And so here is my best attempt at graphing 2 tan x by hand. Let's work on this last column. Same deal. We're going to take the values in the tan x column, and then instead of doubling them, we'll just cut them in half. So this would be -√3 over 2, which is about -0.866. This would be -1/2. This would be -1 over 2√3, or about 0.289. Half of 0 is still 0. And then we repeat the same values. That's a negative. We repeat the same values, but positive. So positive 0.289, positive 1/2, positive 0.866. So we have some symmetry in this graph. I'll plot this one in green. So at negative pi over 3, at -0.866, so I don't know, maybe about there. Then at negative pi over 4, we're at 1/2, goes through 0. Oh, I skipped negative pi over 6. -0.289. It's kind of staying kind of close to the x-axis for a while. At positive pi over 6, we're at 0.86, so maybe there. Oh, 86 is negative pi over 3. I'm going in the wrong direction. Sorry, 0.289. There, I'm back on track, you guys. Positive pi over 4 is positive 1/2. Positive pi over 3 is 0.866. So again, it doesn't really stray far from the x-axis, at least not at first. But it's still undefined. Like, the closer I get to pi over 2 and negative pi over 2, I still get close to dividing by 0. So those are still asymptotes. We get that same behavior at those asymptotes. So our takeaways from this is that we have these asymptotes on either end of the period at pi over 2 and negative pi over 2. It has this sort of S shape. All of these graphs go through 0, 0. And when I graph these, essentially, here's what I do. I say, okay, I know the shape of the tangent function. I know it's going to go through 0, 0. And then I'm going to use the pi over 4 and minus pi over 4. That's where tangent's equal to 1, like the regular tan function is equal to 1. So I use that as my primary anchor. So like, here's my regular tan of x, that's at pi over 4, we're at 1. At negative pi over 4, we're at negative 1. Here's my 2 tan of x, so there's 2 and negative 2. And then here's my pi over 4 when we were at 1/2 and negative 1/2. So I use that as like my primary anchor, that together with the fact that it goes through 0, 0. Because I know the shape and the behavior of tangent, then I just fill in the rest with the smooth continuous curve. So, you know, this shape continues. We graphed the tan function right here in between these two asymptotes, but it would just continue from pi over 2 to 3 pi over 2, from 3 pi over 2 to 5 pi over 2, and so on. But as with most periodic functions, we usually quit once we get one period of it sketched. The same technique, we're not going to do it, but the same technique, you could make a little table to get a sketch of the cotan function. Cotan function is cosine over sine. It has kind of the same kind of behavior. It has also a period length of pi, just like tangent. Only with cotan, we graph from 0 to pi. Its asymptotes happen when sine is 0. So sine is 0 at 0, and at pi it's on the left and right extremes of the circle. So that's why we graph from 0 to pi instead of from minus pi over 2 to pi over 2. With the tangent function, that has its asymptotes when cosine is 0, and that's why we graph from minus pi over 2 to pi over 2. Then we make, we can make adjustments to the graph like we normally would. So if I wanted to graph tan of bx plus c, just like we would with sine and cosine, we take this, whatever this coefficient on x is, and we factor it out. So when we factor out, it's b times parentheses x plus c over b. And when we factor it out, one of the reasons is because then this guy right here, there's the phase shift. The period is given by pi over b, so we take the normal period, right? The normal period for tangent this time is pi divided by that coefficient, and then our phase shift is c over b units. And again, the same rule that if it's a plus, if we're adding inside the parentheses here, it goes to the left. If we're subtracting inside the parentheses, it goes to the right. So let's do an example. We want to sketch y equals tan of 2x minus pi over 4. Now notice I didn't change, I didn't put any coefficient in front, and that's easy enough to accommodate. Like I said, kind of take, they use that primary anchor where tangent is usually equal to 1, and that would just sort of be what I change when I graph. If I change that value, we don't really call it amplitude anymore because tangent technically doesn't really have an amplitude. It's not limited, it's unbounded, right? It could blow up in either direction. So if we start this one out, the first thing we want to do, factor out that 2. What goes in the parentheses if we factor out the 2? That's a good start. I'll do the next one, minus. Pi over 8, yep. You can always check to see if you've done it right, because if you distribute this back in, you should recover what you started with inside the parentheses. So this tells us, let's see, the period is pi over 2. And the phase shift is pi over 8 in which direction? Right. To the right. So with the sine and cosine, once we find the period, we cut it up into quarters, and we kind of do that a little bit first with the tangent function. But the first thing I do is I say, okay, I've got a period. I'm first going to graph this without a phase shift, just like we did with sine and cosine. So I'm taking that pi over 2, I'm cutting it in half, and putting half on this side, half on this side. Those are my asymptotes here for the tangent function. For the tangent function with no phase shift. And since I'm not doing a phase shift at all, I know that it goes through 0, 0. We'll work in the phase shift in a little bit. Then I will find my next halfway mark. So this would be pi over 8 and minus pi over 8. So the halfway here, like halfway to the asymptote, this is like where on the previous page, those were like my primary anchors, where I said, okay, I'm either going to be at 1/2, 1, or 2, depending on whatever this coefficient is. So this is at pi over 8 will be at a positive 1, and at negative pi over 8 will be at negative 1. So here is, I'll do this in gray, I guess. This one in gray is tan of 2x. So now I'm just going to work in the phase shift. Working in the phase shift, pi over 8 to the right, that means everything I'm going to just slide it over by pi over 8 units, including each asymptote. So I've got an asymptote here. Pi over 4 plus pi over 8 is 3 pi over 8. My middle point then, the 0, 0 goes to pi over 8, 0. This point becomes 0, negative 1, and this point becomes 1 at pi over 4. Right, just sliding the whole thing over. So there's my graph in blue. More? Yeah, probably. No, Sydney's shaking her head. Resistance is futile. Okay. 2 times cotan of x over 2. So it's a cotan function. And there is no phase shift here, so we don't have to worry about that. So let's find the period. What should the period be? Not 0 to, well, if it were just cotan of x, it would be 0 to pi. So how do we get, if there's an adjustment to the period, how do we find it? And by the way, how do we know there's an adjustment to the period?
Because something is being done to x.
Say that again?
Because something is being done to x.
Yeah, like we have this coefficient on x. What is the coefficient on x? 1/2. Okay, so we get our new period by taking pi and dividing it by that coefficient, which gives us 2 pi. So now, since it's cotan, we're gonna sketch this out from 0 to 2 pi, from 0 to the end of the period. So there we are. There's 2 pi. There's the halfway. And cutting this up, into quarters, so there's pi over 2, 3 pi over 2. Now the asymptotes, because it's a cotan, are 0 and the end of the period. So the y-axis is an asymptote, and we have an asymptote here at 2 pi. This time, now we also have a coefficient out in front that's not 1. That coefficient is 2, and so that's what those values I'm going to use for my kind of what I think of as my primary anchors. Where does it cross the x-axis? Say that again? Pi, yes. So at the halfway mark. And then at these quarter marks is where it passes through the 2 and the negative 2. Cotan, I'm going to go back here a couple of pages, has like the same basic shape but kind of upside down. So it starts upward and then it comes back down, which means that in our sketch, at pi over 2 will be at positive 2, at 3 pi over 2 will be at negative 2. And there's our sketch. Yes?
How did we know that those are the asymptotes again?
Because cotan of, I guess, say x over 2, since that's what we're working with, is cosine over sine. So cosine x over 2 divided by sine x over 2. Which means cotan has asymptotes wherever sine is equal to 0. So sine is normally equal to 0 at 0 and pi, right, like on the very left and right, but since this is sine of x over 2, x would have to be even multiples of pi in order for the argument inside sine to be 0.
Okay.
Yep. Other questions? Okay. Now, I think I have more fun with the secant and cosecant graphs. I know you're wondering, how could this possibly get any more fun? That's exactly what Andrew's thinking. Yep. So, if we're going to start by graphing cosecant. Cosecant is the reciprocal of sine. So, now, we're going to use some of the knowledge we know about the tangent function, namely, and the cotan function. Like we were looking for places that would make us divide by 0, and that helped us locate these asymptotes, these vertical asymptotes. Well, cosecant is 1 over sine. So that will also have asymptotes, vertical asymptotes, wherever sine is equal to 0. The period of cosecant will be the same as the period of the related sine function. Likewise for secant and the related cosine function. So when we sketch this, I know it'll have a period of 2 pi, and I never sketch a cosecant function without first just sketching the sine function. Like, let's sketch sine. We know how to do that. So we're cutting up the period into quarters. It goes up to 1 and down to negative 1. I'm leaving a little bit of space on either end, so I'm trying not to use up all my vertical space on sine. Oops, minus 1. And sine starts where? At 0, and it goes up from there. So 0 at pi over 2 we're at 1, then we're back down to 0, then we're down to negative 1, and then at 0 when we get to 2 pi. So there's a nice, smooth sine curve. Anytime the sine function is 0, we get a vertical asymptote because it makes us divide by 0. That means any of the times where the sine curve crosses or touches the x-axis, that's a vertical asymptote. So we get a vertical asymptote here at the y-axis, also here at pi, also here at 2 pi. Now, at these peaks and valleys of the sine function, like sine of pi over 2 is 1, right? So what's cosecant of pi over 2? So if sine is equal to 1, we know that cosecant is 1 over sine, right? What's 1 divided by 1? 1. Okay. So these curves agree right here at pi over 2. They touch. Now, as sine gets smaller, when I divide by something less than 1, like when I divide by a half, that means we're doubling, right? If I divide by a third, we triple something. So this is the peak. This is as big as sine gets. So as sine decreases in value, that's going to make the cosecant get bigger, right? Because we're dividing by smaller numbers. And in fact, I know when you're graphing a function, and this is a general truth, if you're graphing a function and your function is approaching a vertical asymptote, it has but one choice. I suppose two choices. It could shoot upward toward infinity or downward toward negative infinity. Those are the only two possibilities. Right here, we know our secant function is positive, right? So as I approach this asymptote, it has but one choice left. It can only shoot upward toward infinity. Likewise, when it approaches this vertical asymptote, it has only one choice, and that is to shoot upward toward infinity. It's positive, and I'm getting close to dividing by 0. Now, if we look at what's happening in the other piece, at 3 pi over 2, sine is equal to negative 1. So what's the value of cosecant? Negative 1, because 1 divided by negative 1 is negative 1. So they touch right here, right, at that extreme, at that valley in the curve. Now, as my x's get close to pi, sine gets close to 0. What has to happen to this graph? It has to go downward toward negative infinity, right? It was either going to go up or down, but the graph is negative here, so it has no choice but to shoot downward toward negative infinity. Likewise, over here at 2 pi. So when we graph cosecant, in fact, it's impossible to graph a full period of cosecant that is a smooth continuous curve, because it will always get broken up by an asymptote in the middle. So here's one full period of cosecant, which is just this part, right? The cosecant graph itself is just these sort of U shapes. But that's how I always graph cosecant. I just graph the sine function first. And I know that the curves sort of kiss at these peaks and valleys, and then they diverge. I do the same thing if I'm graphing secant. I just graph the cosine function. I know the curves have to just barely touch at those peaks and valleys, and then they diverge to their asymptotes. So let's do that for secant. Secant is 1 over cosine. Cosine, we know, has a period of 2 pi. So I'm going to cut this up into quarters. Cosine has a maximum of 1 and a minimum of negative 1. Where does cosine start?
0.
Nope. 1. Yeah, sine starts at 0. Cosine starts at 1. So we start at 1 and then we go down. Then we get to the valley. There we go. So here's our nice smooth cosine curve. Okay. So secant will have some asymptotes. Where does secant have its asymptotes?
Pi over 2 and 3 pi over 2?
Yeah, pi over 2 and 3 pi over 2, because that's where cosine is 0. Now, what do you think the graph is going to look like, let's say, looking at just in this first part, between 0 to pi over 2? Guesses are fine. Like
Would there only be like half of that?
yeah, like half of that U shape.
Yeah.
That's exactly right. So there's the peak. The curves kind of kiss at that point, and then the secant curve says, "See you later. I got somewhere to go." How about in the middle of the asymptotes?
Is it gonna do the opposite of what's going?
Mm-hmm.
Yeah. Meet there and then go down.
Yeah. So they meet here, and then this guy goes down. And then between 3 pi over 2 and 2 pi, we just have the mirror image of what's happening at 0 to pi over 2, right? Basically kind of like the other half of that curve. If we graphed it and extended this, it would just look like more like two continuous curves. Like if the cosine curve, kind of continues down this way. So we could continue and see two full continuous U shapes as well. Andrew's like, I'm ready. Sydney's like, I got it. Are you okay?
I don't know.
I think something's funny and I don't understand it.
I don't know. It's like this. I don't even know. What? I don't know.
We're just
Never
graphing.
expected this.
We're just. You never expected the curves to look like that?
It's just like I've never done this before. Like
Yeah.
I've done the other things, but like
Oh, like
this
the sine
is
and
like
the
a
cosine?
whole new thing.
Yeah, things get weird when you let yourself consider division by 0. Things get weird there. And in fact, if you plan to take calculus at any time, you spend a lot of time trying to invent a way to get around the rule that you can't divide by 0. It says, well, maybe we can't. Like, you can't divide by 0, but you spend a lot of time like trying to create a mechanism that allows you to kind of skirt around that rule. And then sort of just seeing what the implications of that are. If you graph on the calculator, it looks kind of weird. Of course, the calculator won't graph the cosine curve there. So, like, let's say, let me get rid of these. I want to graph secant, so I have to put in 1 over cosine x. I also need to make sure I am in radian mode. And I want to set my window. Our period length was 0 to 2 pi. And I'll let y go from, say, minus 10 to 10. So if I just graph this, it doesn't show you like it doesn't show you the asymptotes. But if you graph this together with the cosine curve, so the cosine curve will be in red, you can kind of see them just barely touching. And you almost get a better view. I'm gonna switch up the, let's say from minus 3 to 3. Let's see what that looks like. Yeah, so that's kind of nice. All right, so one more. Let's sketch a graph of 2 times secant of 4x. Sketching the secant and cosecant functions really are fairly simple if you just make yourself start out sketching the related cosine function. So, so we'll start with sketching 2 cosine 4x. All I have done is change secant to cosine. And we know how to do that. Right, so this has an amplitude of 2. This has a period of, 2 pi over 4, which is pi over 2. So I'm going to mark out, and there's no phase shift. If there were a phase shift, I would just work in the phase shift right with the cosine function. Like, I literally just ignore secant for a second and just transform it into the cosine problem. So there's my pi over 2. I cut this up into quarters, like we do. There's pi over 8. What's this one? Yeah, 3 pi over 8. Right, so once you have the 1/4 mark, the third one is most easily obtained just by counting up, right? So we have 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. I mark off the amplitude, making sure that I give myself room on either side. So here's 2, -2. And this is a cosine, so it starts up at its peak. Oops, I should probably plot the points. Once I have this, then I proceed just like we did right above, right in the previous example. I draw my asymptotes where the cosine crosses the x-axis. I know that the curves just barely touch at the peaks and valleys, and then I draw in like the U-shapes where they go. So here we are. There's that curve, that curve, that curve. So the secant curve is the part in green. But I have a hard time sketching by hand a secant curve without first sketching the cosine curve, to the point where I like literally never do it. I definitely use the sine and cosine as crutches to help me with the secant and cosecant. Don't judge.